our next section. I'll be chairman of this section. It's my pleasure to introduce the first speaker, Amaury Alvarez Cruz. He will talk about Riemann solution for low salinity carbonated waterflooding.
Thank you.
You're welcome.
Good morning for all. I want to thank and congratulations to the organizer because this beautiful conference and the nice place in IMPA. Curiously, of the author stays here today. Anderson, Marchesin and Bruining. I to talk today about the Riemann problem of low salinity water flooding. This is 36 problems. I show you a summary of the physical model, the mathematical model, and the way to construct the build the Riemann solution. And I to do emphasis in one particular solution and some conclusions. It is well known that secondary low salinity water flow can improve the oil recovery, and the order of this improve is around the 5 and 10%. A mechanism that explains this process is that when low salinity is injected in porous media, the desorption of organic material produce more water web in porous media, which lead to the well behavior of the relative permeability. The aim of our work is to quantify this improvement of oil recovery when carbonated water is injected in the porous media, equilibrated with low salinity, and in the porous media with phase, oil phase, and saturated with carbon dioxide. To do this study, we developed a mathematical physical model which take into account ions and thermodynamical considerations. We take into account 7 species. We assume that all the chemical equilibrium in both water and oil phase, and also we have equilibrium between CO2 between phase. This physical is idealization of pre-salt formation in Brazil. We assume also that the flow is governed by Darcy law and conservation law for chemical species in one-dimensional incompressible zone. We take also 3 equilibrium reactions, this one, and another equilibrium reaction for carbon dioxide in between water and oil phase. Gibbs rules indicate that we have 4 degrees of freedom. But if pressure and temperature are given, we have 2 degree freedom. In this case, we take the pH, is the logarithm of activity of ion hydrogen, and the chloride concentrations. The mathematical model consists in 4 balanced laws which express the conservation of total hydrogen, decaying, chloride, and the difference from oxygen and hydrogen. this kind of system of conservation law is particularly interesting because in the flow, you can see that the RC velocity is separated for the phase variable. This system was studied previously by Marchesin, Bruining, and Lambert in another model, but we use, of course, some of the results obtained. These four equations, we have four unknown variables: saturation, pH, chloride, and U, the RC velocity. For Hansen oil recovery, we have interested to solve the Riemann problem, which is equivalent to study the four conservation law when the initial data are piece constant functions. This is the situation that we start. To obtain the Riemann solver, we find a sequence of wave, the rarefaction and Coutinho locus. To obtain the rarefactions, we reduce to solve these eigenvalue problems. This eigenvalue problem, which have three eigenvalues. The first eigenvalues have the wave, Bock-Lever's wave, when the saturation, only the saturation change around the wave. The second, what is associated with this eigenvalue, that we call chemical composition wave. And the third one is associated with this eigenvalue, which we call chloride wave because around this mainly the chloride change. And happen that this is a contact discontinuity, which is very useful to obtain the Riemann solution. All the rarefaction wave are obtained of the solution of the first order differential equation. But to obtain the final solution, we use this good splitting that you can see that the RC velocity can be separated for the phase variables, which splitting is very useful from the theoretical and numerical point of view. Also, we take to take these assumptions. The physical parameter obtained by thermodynamical considerations are such that the third component is zero, and the chloride wave is the discontinuity contact. This assumption guarantees that the compositional chemical wave associated to the second, the first and the second, are invariant of the planes of chloride constants. Bock-Lever and the second compositional wave are invariant along these planes. This is the tool that we use to solve the Riemann problem. Another possible solution of our system conservation law occurs when discontinuity appears. We have a shot that satisfies the Rankine-Coutinho relationship. This relationship reduces to solve the intersection of two surfaces to obtain the curve of Coutinho curve. This is the hard part of our work, to obtain this curve, and is also to use to obtain the Riemann solution. Here is a summary of all the bifurcations and inflections curve. we show you the three surfaces of eigenvalue are equally, and the inflections. You can see that these are surfaces almost parallel to the plane's saturation constants. Another useful fact is that the velocity, we can check that the velocity changes mainly in the direction of saturation. So, to build the solution, we need to take into account this bifurcation curves, surface. I show you a general idea to obtain the Riemann solution given 2 points in the phase space. For example, take 1 point here, left state, and we want to obtain the solution to right state in this plane. The general idea is the following. First, we take the admissible solution in the plane of constant chloride determined by the left state and travel around this plane. For example, here we take the rarefaction saturation wave, one compositional wave, then to jump to the another plane when the right state belong, we need to build the transitional surface. This transitional surface is a foliation formed because with the contact discontinuity of chloride rarefaction. This is the idea. When we take this foliation, we take the intersection of this surface with the backward rarefaction that come from the right state. With this idea, in general, it's possible to obtain the Riemann solution in some case. This is a particular solution, was interesting physical, when we have a left here. The solution consists in the following. We have a saturation or rarefaction up to this point when the eigenvalue coincides with another velocity. We continue with another rarefaction. We take a contact that intersects the plane when the left state belong. Here we first have a constant state, and this one with another constant state, and finally a shot, admissibly shot to the right state. This is the solution for this case. We verify to check that this is the only one possibility of admissible wave to left to right. Finally, we compare the analytical solution with the numerical solution obtained with the console program. This corresponds to the profile of the chloride, and this corresponds to the profile of the pH. We can see that excellent agreement for this chemical wave. For saturations, we obtained good agreements, some difference in this part. Well, in general, we developed a Riemann solver for oil recovery problem for low salinity carbonated water flooding, including geochemical aspects. This methodology is adequate for one-dimensional compressible two-phase flow in porous media with several chemical compounds. We obtained good agreement between numerical and analytical solution, and we show that the Riemann solver can effectively, accurately solve the carbonated water flooding with low salinity injection problem and elucidate the mechanisms for enhanced oil recovery. Thank you.
Thank you very much.